So let's start. So we are very happy to have Pablo Portilla from Madrid. He is going to tell us about vanishing art for isolated plane curve singularities.
Thank you for the invitation, and I feel honored to close the event. It was a pleasure. Also, it seemed like it was so interesting talks that I really forgot about my talk now. Okay, so I just changed slightly the title. On the website, I said vanishing arts. I said the vanishing arts and cycles. So I'm going to introduce.
Sorry to interrupt. I actually forgot. Maybe I wish to thank our organizer
Yeah.
for organizing the conference. Thank you for the wonderful work.
Yeah, I'm really happy. I learned a lot of things these 2 weeks. I'm sure also the first week there were some interesting talks, but for the last 2 weeks I can speak. So I was saying that I included the word cycles on the title now. So I am going to introduce for you the notion of vanishing cycle in singularity theory, how we think about vanishing cycles. I'm sure you have similar or different ways of thinking about them. And I'm going to talk to you about some questions on vanishing cycles and this thing that is called vanishing arts that I will introduce as well. And this appeared in a previous work with Salter and will appear in a joint work with Bai, Cho, and John. So for us, the setting will be that of a representative of a germ transition to C with an isolated critical point. So isolated critical point at the origin. So we say in this case that F defines a plane curve singularity, an isolated plane curve singularity at the origin. And to this data, we can associate a non-trivial locally trivial fibration, which is called the mean fibration. So this is the mean fibration over the cube. So here epsilon is taken small enough that the intersection with the zero set of F is transversal, and also for all other epsilons smaller than this one, the intersection should be also transversal. And delta is chosen small enough with respect to epsilon so that this intersection is transversal as well. And the restriction of F to this space by Erzman fibration lemma gives a locally trivial fibration. This is the mean fibration. So I'm just introducing some notation now. In this space, we have the Milnor fiber. So I will note by sigma any Milnor fiber. So you have to always think of this as an actual the image of this restriction by this restriction of a point in this circle. And since this is a locally trivial fibration over the circle, we have what is called the characteristic diffeomorphism of this locally trivial fibration, which is called the geometric monotony. The geometric monotony. And throughout the talk, I will make several times the difference between some objects that will not have the adjective geometric and that will also have the adjective geometric, and we try to distinguish between those. So when I speak of the geometric monotony, I think about this automorphism as a diffeomorphism on the fiber up to isotopy, and not just the action of this on the homology of the fiber. So absolutely fine. It's a diffeomorphism, and the singularity being isolated. I have to change the. That's
so we don't care. No, keep it. Let's put it on the table.
Isolated. Isolated implies that we can choose this representative to be the identity on the boundary. So we can take a vector field that parameterizes this circle, and we can take the lift so that it induces the trivial isomorphism on the boundary. So selective implies that phi is well defined up to isotopy fixing the boundary. Identity, and then I will summarize all of this as saying that phi is in the mapping class group of the Milnor phi. Okay, so this is the group of isomorphism of the fiber relative to the boundary. Okay. Okay. So I introduce some basic objects associated with a singularity. I'm going to introduce another richer object, which is the versal unfolding of the singularity. So, sorry, the versal unfolding of the singularity. So let F be a representative of the versal unfolding of the versal unfolding of F. Okay, so you can think of this space as this as a vector space. So this is the partial the Jacobian ideal. And now we can create the following spaces. So we can collect the zero fibers of all these functions for each parameter lambda. So we introduce notation. So we denote by f lambda constitute g the map xy to f of xy lambda in the parameter space. And then I can take the following space. Pf is equal to xy lambda such that f lambda of xy equals 0. And I intersect these with say small enough ball as well. So this radius will be chosen in the moment. So I can project these to the parameter space, so mu. And now I can think about the points here, which give me a singular fiber. So I have here the discriminant, which is it's a hypersurface, and that see, and then let me just say that. And well, if I remove those problematic points and I restrict, so I take a small polydisk here and I intersect with a small enough ball here, then this will be a locality observation restricted to the complement of the discriminant and it's the image that is mapped. So I can take PF the discriminant and these two small disk. This contains simu. So this is a locality observation. And well, this I have a locality observation, so I can think about its monotony representations. So I can take the action of the fundamental group of this space acting on the mapping class group of the fiber. So I can take a monotony representation that goes from by one of and I can define the image. I can think about the image of this homomorphism and give a name. So let's say MIF will be the image of rho, which is a subset, a subgroup. And this is what I call the geometric rho. So the whole game here is to try to study this group in one way or another, and some objects associated to this group. So let me introduce vanishing cycles now that we have the setting. So we have here C mu, and we have here the discriminant. I take a point, lambda outside the discriminant. Here I have sigma lambda, the Milnor fiber. And I can take a point, path, sorry, that goes from this point to a smooth point of the discriminant. So let's see that this is smooth point of the discriminant. And it happens that over smooth points of the discriminant, what lies above is a nodal curve, with exactly one node. So here it's going to happen. So it's going to be like something like this. Or like locally near one of these points, I'm going to have the model of the Morse singularity. So here in a neighborhood, and neighborhood of this point. So now I can take here a small ball. I can look at the Milnor fiber of this in a nearby fiber. It's going to be a cylinder because the Milnor fiber of this singularity is a cylinder. And I can parallel transport this to this fiber. It's going to give me here along this path a cylinder. And this cylinder is going to have, well, a cylinder gives you automatically, by definition, an isotopy class of a simple closed curve. For instance, this one, which gets contracted to a point along this path. So call C a geometric vanishing cycle. Okay, so a geometric vanishing cycle. This means that it is an isotopy class of simple closed curves.
There's no specific way. I mean, if you do like a parallel transport, you can actually pick a particular representative. I mean, if you don't want to.
This is a good discussion that I had this week. There is this. So, if you have a symplectic form, which I do in this case, of course, then you open the book by Seidel, for example. I mean, there are many references, and it tells you. So you take this path, and now you take the unique Lagrangian that lies above this path, that defines the boundary of the Lagrangian would be on the fiber, and the Lagrangian has one point over this point, which is what is called the left-side symbol. This is the unique Lagrangian, and this gives an exact Lagrangian, which is the vanishing cycle. This is what you mean. So I tried to work out the details. I couldn't prove that there exists a unique Lagrangian that satisfies those properties, and I couldn't find a proof of this statement. So I know the sentence that says that take the unique Lagrangian, such and so on and so on. I don't know how to prove. I think I'm close with the ideas that I have to do this. So you have to take the symplectic connection. You have to take the set of separatrices of the vector field. So you take this vector field. And you lift this vector field with the symplectic connection. This gives you a set of trajectories that converge to this point. And now I would like to say that the union of these trajectories is a manifold. I'm not able to prove that the union of these trajectories is a manifold. I am able to prove it in a particular model. So if I take this singularity in particular, I can prove it.
But it's assumed that it is that singularity.
Up to change of coordinates. If you change the coordinates, you have to take the Poolbach of the metric.
No, I think it's assumed that it's standard.
Double point, yeah.
Yeah, good point. That's an assumption of the book.
But also the path is not unique, so it's...
But the path is no. You have to take at some point. You have to use Moore's lemma. You have to use Moore's lemma. You cannot get away with saying that this is always in. What does it mean that this is that point? You have a map from the space to the disk, and then you look at the point. What it means that it is this one. The only thing that I know is that the Hessian is non-degenerate.
No, it's the thing. It's no more because it's assumed.
It is.
It's assumed to be more.
Okay, so in that case, maybe that's the subtlety that I missed. If this is a particular model, then yes, I can put. But if not, which I am not assuming, because I take which is not true in this case, I cannot do that. So in this case, I cannot do that. But what the general theory gives me is an isotopy class of a simple closed curve, which is the geometric vanishing cycle. But thank you for the. Maybe now I will read a little bit differently the book I cited. But in this case, it's safe enough for me. And then C, meaning the class here, it's a vanishing cycle or an algebraic vanishing cycle. Okay, so geometric vanishing cycle, the procedure is this path. This path selects an isotopy class. The isotopy class is the geometric vanishing cycle. Each class in homology is the algebraic vanishing cycle. Okay, so why are these elements important? Well, some of you have some personal motivations to study these objects. In particular, in the case of singularities, the entries around these objects generate the geometric monopody. So one good enough motivation is to entries around geometric vanishing cycles generate. So, for that reason, one good question that I can pose now is, well, I have to go through a lot of a long construction to be able to consider vanishing cycles. I would like to, just by looking at a Milnor fiber, somebody gives me a curve in the Milnor fiber. I'd like to know if that curve is a vanishing cycle or not. So, say, question detect vanishing cycles. Geometric vanishing cycles. Okay. Just a remark. This notion is strictly stronger than this one. So we are able to prove that for any algebraic vanishing cycle, you can find a simple closed curve that represents it that is not a geometric vanishing cycle. So not every representative of simple closed curve is inside an algebraic vanishing cycle is a geometric vanishing cycle. Okay. Any questions so far? So I want to understand this, say, the set into this equation, the set of vanishing cycles, the set of simple closed. And this is something that is strictly contained here. And so this is an infinite subset of this set. It's infinite as long as the singularity is not A1 in all the cases. So infinite subset. Okay, so this is one thing. Another thing is the following. Let me introduce the second part of the problem, then I will give answers. Let me introduce the variation operator. So because I have a diffeomorphism that is identity on the boundary, this is the geometric monodromy, I can define the following map from relative homology to absolute homology. Takes a cycle here, a relative cycle, let's call it A, class of A. I take some chain that represents this cycle, I compose that with phi, so I apply phi to that chain, I take minus A, and I take the class of that. This, because this property tells me that this map is well defined. And there's a theorem that isolated, again, the fact that this comes from isolated hypersurface singularity implies that this operator is a linear isomorphism. So, well, typical picture, you have something like this. Let's say that we have here the singularity again, and now we take the geometric monodromy is a right-handed twist that puts this cycle to this cycle. And so if I take now minus A, this gives me a cycle, which homologous to this cycle here. Okay. This is A, and the blue cycle is bar of A. So the question here is, now I have a much more complicated linear fiber, and I would like to understand the inverse of this operator. So if I have a good knowledge of the geometric monodromy, and there are good models of the geometric monodromy, then it is as difficult as knowing the geometric monodromy as it is to compute the image. But computing the inverse, if you try to think about it, it's not that easy. So if I give you some curve here, and I ask you, can you give me an arc that is sent to this curve by the variation operator, then the problem is not so clear. So since I have a predetermined set of elements here, I would like to know what is the counterpart in the relative homology. And furthermore, I would like to define, I'm going to define a homotopy version of this variation operator to capture these subtleties between difference between a geometric vanishing cycle and an algebraic vanishing cycle. Yeah, I'm going to define a geometric version of the variation operator. Not this one, yes. I had to introduce this one in case some people are not familiar with the Bayesian operator, but I will introduce now the geometric version of the Bayesian operator. Because this, of course, well, if you know this as a linear, well, everybody knows how to invert a matrix, right? Okay, so geometric Bayesian operator. Just to make sense of this question precisely. So let me consider this is going to be the set of closed curves. I'm going to ask that these are piecewise C1. And this is going to be a homotopy. So closed curves are homotopy. Then I'm going to define also a set of properly embedded arcs. So these are going to be properly embedded arcs. Say, and I ask that the boundary of the arc is sent to the boundary of the fiber. And the interior. This is a C1 embedding. And also, I'm going to consider this set to homotopy fixed in the boundary in this case. Homotopy, which is the identity on the boundary. Now, this is going to be to play the role of the relative homology, and this plays the role of the absolute homology. They can define the operator P goes from here to here, takes an element to so this is concatenation of paths. And this gives me a closed curve here. And now I can pose this question more precisely. So the following is true if I take any element here. This element can be represented by a disjunct union of arcs. And now given a closed curve that represents an element in homology, I would like to find which is the collection of arcs that is sent to this homology, to this curve. Any questions about this? Now, definition A here is a geometric vanishing arc if the A is a geometric vanishing side. Okay. So now I will start giving answers to these two questions. So for the first one, I need to introduce the following notion. So let's say I'm going to call a frame mapping class groups. So for the purpose of this talk, a frame mapping class group is going to be the stabilizer of a nowhere vanishing vector field defined on a surface, on a linear fiber. So let me say I take a nowhere vanishing vector field on sigma, and you can think of sigma just being any topological surface with boundary, or differentiable real manifold of dimension 2 with non-empty boundary. I have a nowhere vanishing vector field. Now I can think of the following. I can think about the elements in the mapping class group of sigma such that is isotopic. Okay, and I'm going to denote this momentarily by this. Let me just say a few isotopic through nowhere one. Yes, isotopic. Or let me just say homotopy, because some people homotopy along nowhere one is otherwise. I'm not saying nothing. Otherwise, vector fields. To any such nowhere vanishing vector field, I can associate a winding number function that captures everything I need.
Suppose anything about that, how it's the boundary that they are.
No, I don't impose.
The boundary that should be.
No, actually, I cannot. There is not. I mean, the strongest condition I can impose on the boundary is that it is monotone, in the sense that it always turns in the same direction. But I cannot impose that it points outwards or inwards. This is determined by the topology of the surface. You can see this very clearly in the case of one boundary component. The winding number that I'm going to define now, in the case of one boundary component, has to be exactly the Euler characteristic of the surface. If you have several boundary components, you have some freedom to choose, but not a lot. So I cannot ask that I mean, it's impossible that the vector field always points outwards or inwards. So but one thing that is interesting to us is that it is monotone. This you can. So one dynamic function. So let me say C in C simple closed curve. C +1, 2, sigma simple closed curve. And then I can associate to this a 1D number, which is defined as I C, going to be the integral over S1 of the differential of the angle function between the two vectors that I have on the curve, right? So I have here my the curve C. The curve C has, say that this is an embedding, C1 embedding. So here, at each point, I have two vectors. One is the forward pointing vector of the parameterization of C, and I have the restriction of the vector field here. So I can measure the angle at every point, and I can measure the differential of the angle, and the differential of the angle of what? Of C prime of T and psi of C of T. So this is going to measure how much this vector field winds around the other one. That's going to be an integer. So this is the winding number, and depends only on C, on the isotopy class of C. And it turns out that if I have, so this captures all the information of the vector field in the following sense. If I have two vector fields, two nowhere vanishing vector fields, then this one is homotopic to this one along nowhere vanishing vector fields, if and only if the associated one-dimensional functions are the same. This one-dimensional function captures all the information. And you only need to know this one-dimensional function on a collection of curves that generates the homology. That is enough. Okay, so now after this brief introduction of what is a frame mapping class group, I'm going to introduce this other. After this discussion, I can also denote this by mod of sigma of phi. Phi is on one number. Okay, so now let's look for a vector field in our Milnor fiber. Any questions about that? Okay, so turns out that we have a canonical vector field defined on every fiber of the versal unfolding of a plane curve singularity. So the observation is the following. You can do this fiber-wise. On C2, we have the complex symplectic vector two-form. Complex symplectic form dx y, and I have the function f, so I can compute the Hamiltonian vector field associated to the function f and the symplectic form omega. F psi f is the Hamiltonian vector field of f with respect to omega. Then, well, in your computation, this is our vector field, and now I can state the results that will solve the first question. So let me then theorem, and then we have a little discussion about this theorem. The theorem, example, if f is not of type an dn, and the genus of the Milnor fiber is at least 5, then I will say something about this hypothesis. Then A, the geometric monodromy group is this group, and B, a simple closed curve C is a geometric vanishing cycle if and only if phi C is C. So now we have this vector field on the Milnor fiber, and just computing this line integral tells you if a simple closed curve is a geometric vanishing cycle or not. So about the hypothesis, let me first say that if the singularity is of type an or dn, the theorem is false. This fails. So this is always true. This is always true without hypothesis. True. And also, this is always true. For the other implications, we need the hypothesis. For the case of an or dn singularities, the theorem is false. And if the singularity is not of type AN or DN, there is only a finite family of 6 singularities that have genus smaller than I. So there is a small family for which the theorem does not say anything at all. For all the other singularities, the theorem holds. So these is not hard restrictions. So we're going to have more discussion about this theorem, but first I would like to answer questions if there are any. The geometric monodromy group is the stabilizer of this vector field, and we can detect vanishing cycles like this.
So, did you actually define the geometric monodromy group? Is it the below subgroup that I
The geometric monodromy group, I defined it as the image by the representation row. So I had the representation row from the fundamental, the complement of the, from the fundamental group of the complement of the discriminant.
It is.
You can also define it by taking any morphification by Hamlet theorem. So it is not necessary to go. I gave the actual definition then.
Okay, yes, you did.
Okay. So first time I spoke about this result, Andras Nemeth asked me what is the statement in higher dimensions. At that moment, I had no idea how to or even a conjectural statement in higher dimensions. Now I can say something. So I will say it for the first time, but maybe it's interesting for people here. So I learned that during this week that a form that I call the general Belfan-Leray form, it is called also the Calabi-Yau form. So the problem to generalize this to higher dimensions is that in higher dimensions I don't have a selected complex symplectic form. And now I can think about this. Let's call it omega sub f. It's going to be dx wedge dy divided by df. So this defines a relative one form. This is a one form when restricted to each Milnor fiber. So this is relative one form, and in particular it is omega f form. And now, in this particular case, when sigma has complex dimension one forms are in bijection with vector fields without the presence of anything. Just they can define by duality the vector field such that omega of f sigma applied to this vector field is the function constantly 1. So this defines this vector field. And it turns out that the dual to this one form is precisely that vector field. So if I don't say complex symplectic form, and I say in general, I have these, I take the form defined by.
I'm sorry, how do you define the vector field? This does not define the vector field.
Because of dimension reasons. So if you have a one form, so let's think it about on each the tangent point at each point. So if I take a P is a point sigma, I have this. This gives me a linear form from this space to C, which is a linear isomorphism. So this is at the point P. This is a linear isomorphism. So I can take the image of the point 1 here. This gives me a vector here. So this formula defines a vector field on the surface sigma. And this is This is only for dimension reasons. And in higher dimensions, this is not true. In complex dimension 1, it is true. If I have a non-degenerate complex value to one form, this gives me a vector field. Again, this is by this one, there is only one. So this yoga is confusion, but this is correct. The trick is, like in higher dimensions, we have to forget about vector fields. We have to think about this form. Now, at least one can try to conjecture that the geometric monodromy group should be like the stabilizer of this form.
It's a gradient on the symplectic manifold. And this is the Maslow's theorem.
Yeah. I'm using the language that I mean, this is something that I learned very recently. So to me, it's very interesting that the conversations this week, because I saw how. So this is, to me, what I learned is well fun that I form, and to me this is Andrei Sadevchenko, volume 2, and the last chapters, probably like, I think around chapter 7 it does this in the real setting, but then chapter 10 deals with this one. So this is why I also, in the beginning, I was thinking about giving a talk directly on the second part, so the part that I'm going to talk about now. But I decided that maybe after the talks and the conversations this week, this part would also be interesting for the other community. So people from Singularity have already listened to this before, but any other questions about this?
So will you say something about this in higher dimension?
No. Well, I can say, but this is written nowhere. This I don't know. Don't even know how to. Maybe we can hook up the National index and probably.
Are all which Lagrangian spheres are?
Yeah. This is a question that I don't think. I mean, this is by far not known. I can say that this is not known. If I give you a Lagrangian sphere, is it a geometric balancing cycle of the singularity or not? Just by looking at the Milnor fiber. I don't know how to answer this question in higher
This is
dimension.
Donaldson's conjecture, but it was also resolved. It was also wrong.
Yes, but it's just one particular very explicit example.
So what was the conjecture?
The conjecture asks whether any Lagrangian sphere comes from is a geometric balancing cycle.
Any Lagrangian sphere.
Yeah.
Ah.
In higher
This is it?
dimension.
No, even in this dimension, this is false also. Like not every here I can give you examples of because of this of simple closed curves that are not. Here every circle is a Lagrangian sphere because of dimension reasons, and not every circle is a balancing cycle.
Then it's the Maslow assumption is
Probably the suspension gives the very similar formations.
Yeah, probably you can finding a counterexample here. You can find a counterexample taking the suspension. I don't think that.
no, but it's like the conjecture is not for fixed family. It's like you can hook up any degeneration that you want. Can you realize every Lagrangian sphere as a vanishing sphere of some
That is universal deformation.
Universal deformation.
from the singularities side? It's universal, not from the smooth fibers side.
But you're not
Give me
topological.
smooth
I'm sure it
fiber.
has to consider some structure on the fiber. What did you start with? Not
So you have
topological.
just a symplectic manifold, maybe 4-dimensional,
No complex
Closed.
structure.
closed symplectic manifold. Is every Lagrangian sphere?
I say global conjecture. Nice argument.
Yeah.
It's a closed symplectic.
So you want
Okay,
to,
I didn't.
you want to find a lecture.
I think it's conjectures for closed, right?
Yeah.
Okay.
The counterexample is close to.
Yeah. There's a counterexample. But this was like 6 months ago or something. 1 year
years
ago,
old.
maybe.
When we
1 year ago.
Okay.
actually there was a, so I think earlier there was a counterexample that is proved to be wrong later on. And then so it's kind of this problem resurfaced to the community. And then it's, so that's why someone try hard to attack and find a counterexample.
I was not aware of this. Okay.
That is good one. That's the good one. That's the good one. The wrong one is more than 10 years.
So the wrong one was.
It's like Ivan Smith tried, but up to like some number, and he did one more something like this, like something.
So theorem with the same hypothesis. A single properly built arc and VA is a geometric balancing cycle if and only if the geometric intersection number between A phi of A, phi is the monotony, is 0. Okay, so this is geometric intersection. So what this means is that I take all the arcs that represent A up to isotopy, all the arcs that represent phi A up to isotopy, fixing the boundary both, and I count intersection numbers. I take the minimum of those. This is a well-defined number, and when this number is 0, then the image of A by the variation operator is a geometric balancing cycle. So, while proving this, I realized that there is some subtlety that is not attained by this theorem, and the subtlety is the following. I can take it.
I miss it. What geometric intersection number is?
I said it by words. I'm gonna define it on the right. Let me see. A, B are here. A, B is defined as the minimum of the following non-empty set of natural numbers. A prime isotopic to A relative to the boundary, B prime isotopic to B relative to the boundary, and then I count intersection points between B prime. This is a subset of the natural numbers that is not empty. Take the minimum. That is the definition.
So the boundary can move.
No.
And at the crossing,
No.
it can
A
move
prime.
across.
This means that there exists an isotopy that takes A prime to I relative to the boundary. Relative to the boundary, it means I cannot move on the boundary. I count intersections. I count intersections on the interior. You know, otherwise it's true.
So you don't move the boundary.
Otherwise A and phi A intersect always on the boundary because phi is the identity of the one. So this is how you define. So this is far Margalit. It's chapter 1.
But phi of I also represent an absolute homology class. So what is the relation?
This is not defined on homology classes. It's defined on
But my question is, phi of A, because phi is, no, it's not, I see.
Phi of A, what?
No,
Okay.
I was confusing with bar.
No, bar, no. Where is the bar?
What is the first bar? Oh,
What is the question? So I was talking about a subtlety here, which is, I'm able to find using a theorem by Reiner-Kendner, which is also used in the proof of this theorem, I'm able to find the following. So let me just here the subtlety. There exists simple closed curves. So there exists, let me just read. So this is clear. There exists A, and this one, simple closed curve C. The class of C non-zero, and such that C is not the image of a single arc by bar, by the model. So even though var is a linear isomorphism, when I take the geometric variation operator, I can find simple closed curve that is not achieved by just taking the image of one arc. So that means that we may be missing some geometric vanishing cycles by only considering images of single arcs. So that's why I extend my definition of geometric variation operator to something defined on the Zion union of arcs.
I have a question.
Yes.
So B, that one B depends on the vector field, right?
Which one? B.
The theorem B.
The theorem B. Yes. Here is the vector field. This is the winding number function.
But then this theorem doesn't depends on the vector field.
It does. It does. It is not. So I can give you a proof of this theorem if you want.
But the vector field is not in the statement of the theorem.
It is not in the statement of the theorem.
It's in the statement of that theorem.
Yes. And
you're using the vector field to define the intersection numbers?
no, I'm using the vector field to see that this condition implies that phi of var of A equals 0.
But the vector field is definitely a vector
So
field.
let me just write the following.
It's when there is
Let me then it will appear on the statement. This is a condition that can be checked if var of A is a simple closed curve. So if var of A is if phi of var of A is 0. So if phi of var of A is 0 and var of A is a simple closed curve, then this condition holds. And then this condition holds. If you want, you can put this in the middle, and then it is on the statement of this theorem. Let me just write it here. If var of A is a simple closed curve, there is something that needs to be defined, and it's non-separating, and var of A phi var of A equals 0. This is satisfied if and only if this is what I used to prove it here. An important consequence of this, and this is where you see, is that I can only, if I arrive at a simple closed curve, it is necessarily a geometric vanishing cycle. So if I start with a properly embedded arc I apply the variation operator, and what I obtain is a simple closed curve, then it is necessarily a geometric vanishing cycle.
I think what you were confused about was because it seemed like this. I think this is just a special grading. Like it's a canonical grading that he's using. So,
Of course, like it is. There is nothing wrong with not appealing the. I mean, actually, that's part of the, in my opinion, that makes the theorem also interesting. Is that you can write it without appealing to the canonical gradient. You can just verify if the image of A and phi of A do not intersect, then it is a geometric vanishing cycle. So just let me. Any other questions? Okay.
so what's an example of this? Is it easy? Subtlety.
A subtlety. Yeah, it is easy. You see? This is if I need to check exactly how many, in order to make it correctly, how many genius.
I can ask after.
Oh, it's something like as follows. So I was able to compute it. So if I have, so this is singularity test, and I have genus 5, and it's going to be minus probably something like this. I have to look at it. Maybe 3, 4, and then the curve is. I don't know if it has genus 1 on one side and 4 on the other, or 2 and 3. I can produce this. And this can be, so there exist, what it means that there exist examples of this phenomenon happen. Not for every plane curve, but they do exist. You need at least to have 2 boundary components to produce this kind of contour examples. So there are candidates for, there are candidates for, and even more. This is even more something satisfies something more, which is the winding number of this curve is 0. But you need the curve to be non-separating to be a candidate for a vanishing cycle. So this is a candidate for a vanishing cycle, but it is not a vanishing cycle because it is separating. It's a candidate because the winding number is even 0 in this case.
How can you prove something like that?
How can I prove
How
that?
can they prove this? Okay, I'll
Because of the following. So the game.
Just to say that, so maybe a few more minutes.
I can finish now, and we can have a discussion where we want to have this now. So I finish now. Thank you.
Oh, okay.